So this is the last section of the last chapter of the last math class you're probably ever going to take. Section 5.4 talks about annuities, present value, and amortization. And the difference between 5.3 and 5.4 is in 5.3 we were looking at deposits being made, money putting into account, and looking at the future value of that. In this section we're going to talk about annuities that begin with an amount of money and to make regular payments out of the account. So the present value is the amount that needs to be deposited today in order to make all of those future payments for the term of the annuity. So it's a rearrangement of the formula for the present value of an ordinary annuity. And notice that the exponent is now to the negative n power. And that has to do with that we're using the formula the other way around. We're saying how much money do we put in at the beginning so we can make all those payments. So here's an example. Find the present value. So find the present value. Ordinary annuity. So look for that word ordinary and know that means payments are happening at the end of the period, the same as in the previous section. So your payment amount is $10,000. Then just look carefully at what's similar and what's different in the formula. So I still have in parentheses a 1 plus and the I. So we need to write that as a decimal. So it's going to be 0.075 as a decimal. And then semi-annually, so divided by 2. Then there's a total of 30 times you compound. So negative 30 is going to be the exponent. And then always dividing by the same I as you had in the numerator. So when you do this, hopefully you also will get 178,292.45 as the amount that you need to put into an annuity account. So this is called funding a pension. If you've heard the term unfunded pensions, it's we didn't put the $178,000 in there. But this is how you would fund a pension account. You would put that money into an account and then it would pay out the $10,000 semi-annually. So we can also solve this equation for payment by dividing by this amount in the big square brackets. So let's write the formula the same way and just solve for the opposite amount. So I want to find the present value. Whoops, find the payment made, sorry. The present value is $45,000. We want to find the payment amount. 1 minus 1 plus. My interest rate as a decimal will be 0.053 compounded monthly, so divided by 12. Then I'm doing monthly payments for 11 years. So that's going to be 132 payments. So that exponent is negative 132. And then we divide by that same I. And how I would do this is I would calculate out this part in the square bracket, and then I would do 45,000 divided by answer. So however you do it, you need to get that the payment amount is $450.62. So make sure you figure out how to get your calculator to give you that result. Okay, so one way for a bank to think of a loan is in the same way as thinking of an annuity, and they can think about it as you borrow the present value and then you make payments until the amount you owe is zero. So it's just another way of thinking about it. So when you do it this way, you call these amortization payments. The loan is amortized. And if you have a loan and the loan amount is the present value dollars, then it's just a rearrangement of the previous formula and another way of thinking about it. You can see that really it's the same formula from above, solved for payment. So we can find the payment necessary to amortize a loan of $41,000. Have 1 minus 1 plus, my interest rate will be 0.09 as a decimal, over 2 for semi-annual payments, to the negative 10 semi-annual payments, over always the same interest rate. And we get 5,181.53 as that would be the amortized payment amount for that loan. Okay, then this is of small importance, but might be interesting to you personally, actually. It's a way to estimate the remaining balance on a loan. So first, we're asked to find the monthly payment. So that's exactly what we just did previously. That's this amortization payment amount. So we're going to use that formula again and say the payment is going to be the $15,875 that you're borrowing divided by the 1 minus 1 plus, your percent is 2.89, so that's 0.0289 as a decimal. And we're doing monthly payments, so divided by 12. And then your exponent is going to be negative 36, because you're doing 36 payments monthly for 3 years, divided by the same interest rate. And this is the amortization from the previous formula. And we get $460.90 as the monthly payment amount. So that's find the monthly payment. Okay, now we're going to use this new formula and find the remaining balance. So it's a lot of the same numbers we've already been looking at. Here's where the difference comes, is in the exponent. And the exponent is minus n minus x, where this x is after x payments have already been made. So in this example, they're asking for the remaining balance after 1 year. So x is going to be 12 because you've made 12 of the payments. Okay, so we can find the estimated remaining balance by taking our payment amount that we figured out, $460.90, big square bracket, 1 minus 1 plus 0.0289 divided by 12. Now the exponent is going to be negative. It was 36 minus the 12 payments that we've already made. And then divide by your same interest rate. And you should get $10,735.44 as your remaining balance on this loan. Okay, then there's just a couple more things in this section. One is making sure you know how to read a schedule. So this is an amortization schedule, which it's pretty obvious that it was made on a spreadsheet, like an Excel spreadsheet. And it's just a schedule that you could give this to somebody who borrowed money and they could see exactly how all the money was being applied. And so, for instance, we're trying to get our house paid off earlier. And so you can make your own schedule where you can say, well, what if I apply more to the principal each month, and how does that change the schedule? So on this schedule, it was $1,000 that got borrowed for a year at 12% interest compounded monthly. So use the schedule to answer how much of the fifth payment. So here's the row that's the fifth payment. how much of the fifth payment is interest, and we just read it right off of the schedule, $6.80. And chances are really good that if you're going to go into finance or accounting, you will be making schedules. It's just a very, very common, useful tool. So the next question says, how much interest is paid in the first 5 months? So here are the first 5 rows. So here's the interest paid in the first 5 months. And hopefully you're seeing how easy this would be to do with a spreadsheet. You would just say, what's the sum of these 5 numbers? And when you add them together, hopefully you get 4204. And then the last question is, how much interest do you pay in the last 5 months of the loan? So here are the last 5 months. And let's look at that interest amount. And I always think it's kind of interesting that look at how much interest you paid in the first 5 months. The bank's getting a lot of their money back at the beginning. And then over the last 5 months, then you're starting to pay off the loan amount and pay less interest. Okay, then the last thing we're going to look at is not super common, but I want you to have seen it. So we had ordinary annuities and the feature that was important about them was the payments made at the end of the period. And then we have annuity due, and this is just kind of archaic language that has persisted. Annuity due is the payment made at the beginning of the period. So this is consistent in 5.3 and 5.4 that the word ordinary with annuity means payment made at the end. The word due with annuity means payment made at the beginning. But notice that in each of the formulas, they make sure and tell you that in the words that tell you what the letters are standing for. So just pay attention to the words in the problem. It will either say annuity due or payments at the beginning, and that's how you will know this is your formula that you use. So this example I think is kind of interesting because it's a lottery question and it's saying, suppose you take your lottery money, and this information's left out here, but this is over a 30 years period. So they take the $207 million and divide it by the 30 years and say those are payments of $6,900,000. But they're made in the future. But we'll give one to you at the beginning of each year for 30 years. So the question here is, how much is that worth today? So if somebody offered you a flat amount today to take over your lottery jackpot winnings, how much should they offer you for you to want to say yes? So let's figure that out using this formula where we have what would the present value be of 6,900,000 plus 6,900,000 times 1 minus 1 plus interest rate of 0.0578. And it's not said otherwise, so I'm going to assume that's annually, to the exponent of negative and then 30 minus 1. So 30 years minus 1 over that same interest rate. So what you come up with as the present value of those payments is 102,877,051. So there are people around who would say, how about if I give you 100 million and you give me your jackpot winnings over the 30 years? And you might say, okay, because I'd rather have the money now. And it's pretty close. But if somebody said, I'll give you 50 million, you should probably say, no, I don't think so. So this is a way of saying, what is the value of all those future payments if I had the money today instead? And that's it for section 5.4. It's been fun. I hope you had a less than horrible experience.